All right, let's get started. The folks in concrete design already saw this, so I'm a PNR fan, so I find the show hilarious. Okay, so you all have a weld homework due on Friday, but I'll open up questions on Wednesday. But I've already talked to a few of you, and there's a good number of you that have already finished it. It's really short, so because again, like I could have done like 6 problems that were all the same, and there's just no point in making it longer. Okay, so but are there any questions? Okay, one other quick announcement, and I'm just curious if anybody's around, but Marshall is hosting the Science Olympiad. It's sort of a competition for middle schoolers and high schoolers. It's this Saturday. If anybody is around, we could use a few volunteers and whatnot. Just do me a favor and let me know. But I'll make sure and bring it up here within the next couple days. It's a pretty easy event. There's sort of a civil engineering themed event where the students are bringing in these sort of like balsa wood cantilevered bridge things, and so we'll test them to failure and record the capacities. If you were involved in volunteering for the West Virginia Bridge Design Competition last spring, it is nowhere near that grand scale of an event. That was a production compared to this. But if you're around, we could use your help. So, okay. Let's go back to columns. So last time, if you recall, we derived, we basically re-derived Euler buckling from mechanics of deformable bodies, and then we started to chip away at why Euler buckling, I want to say is wrong, but it's not good enough. Okay. Now, there's a couple things that we can handle through the use of effective length factors, those K factors that we discussed last time. And then there's a couple of things that we can handle just through our structural engineering practice, like ensuring the loads through the centroid and trying to ensure there's no twisting or shear, which isn't a big deal with W shapes and whatnot. So there's a few things that we can handle sort of in-house. But there are 2 primary phenomenons that basically say that, I mean, you can handle some things, but there's 2 phenomenons that Euler buckling just cannot handle on its own. And somebody remember what those 2 phenomena are. Somebody name one of them. The residual stresses, the locked-in stresses in the I shape from differential cooling. Which, here's something, before I ask about the second one, here's something that I didn't really like, I wasn't very eloquent on this. From here on out, we're pretty much only going to be using W shapes, just for the rest of the semester. And the reason why is because from here on out, we're talking about columns and beams. Columns and beams are W shapes. Now, that's not to say that you couldn't use an angle or a channel or something like that in compression, but primarily W shapes, I-beams are what you're going to be looking at. So W shape, we're basically going to be using W shapes for the rest of the semester. So if you hear me sort of reserve our discussion to W shapes, that's why. Okay, so we said, so presence of residual stresses, that's one big reason. What's the other big reason why real column behavior deviates from ideal column behavior? Imperfections. The idea that the geometry of the column is not perfect. It is not perfectly straight. It is not perfectly plumb. There's always a little bit of variation. So what the AISC model for column capacity does is it accounts for those variations through the following expressions. So just so everybody is clear, this dashed line that you see right here, this sort of circular dashed line here, that is Euler buckling. That's what we derived in class, and this is just cut off at Fy. That's what we derived in class, but that's not what we're actually using. What we're actually using is the solid line down below, and basically it's a piecewise function. If your slenderness is less than or equal to this value, then we're in inelastic buckling. If it's greater than, we're in elastic buckling. Now, how do you come up with 4.71 square root of E over Fy? You just take these 2 equations, set them equal to one another, and solve for slenderness, and that's what you get. So there's no real magic behind that value. That's just the delimiting value as to whether or not we're in inelastic buckling territory or in elastic buckling territory. So The idea is that the column gets really, really slender and really, really long. You're really not going to have much yielding, and it's going to buckle like a rubber band. It'll buckle and it'll snap back to the way it was. That's elastic buckling. So the elastic buckling capacity is just 0.877 times what we derived. That reduction is to account for the imperfections. However, if we're in inelastic buckling, which is, spoiler alert, where most of our columns are going to be, then our capacity is computed as follows. Remember, that fraction that you see there, that's an exponent. Okay? So our capacity is the phi value 0.9 times this critical buckling stress times the area. So it's 0.9 times a stress times an area. And the stress is computed depending upon whether or not your slenderness is less than or greater than that delimiting limit of 4.71 square root of B over Fy. If we're less than that, we're in inelastic buckling range, and here's your capacity. If we're greater than that, we're in elastic buckling range, and this is your capacity. Remember, that fraction is an exponent. It's not 0.658 times Fy over Fe. You compute that fraction, and then it's 0.658 raised to the value of that fraction. Now, when you open up the spec, you're going to see this term L sub C pop up. L sub C is just the effective length of the columns. That's just K times L. And we'll, sort of clearly define what that is later on. And don't worry, we're going to discuss that ad infinitum. The elastic buckling stress is just pi squared E divided by the slenderness squared. Now, that's what we derived. So I don't want you to think it's not useful. It is certainly a useful parameter. It's just not good enough. So we use that to compute either elastic or inelastic critical buckling stresses. Okay, and this is where we left off last time. Now, I'll try and go a little bit slower on the math last time than I did. I'll try and go a little bit slower, but let me be clear. I don't expect you in this derivation to memorize every step. I'm not trying to do that. In fact, the next slide, I just sort of give you an equation, say, just trust me, this is the equation, because it's a pretty tricky equation to derive. So what do I really want you to understand? Here's what I really want you to understand. First off, I want you to understand what local buckling is anyways. Okay? What is local buckling? Local buckling is when an element of the cross-section fails before the entire section does in a stability-related failure. So, we're all pretty familiar with global buckling, the entire column failing in compression. But what if it's not the entire column that fails? What if it's just a flange that fails? What if just the flange buckles or the web buckles or something like that? That effect, we have a name for that, and we call that local buckling. Not the entire column failing, but an element of that column failing. So like a flange, a leg of an angle, something like that. Now, in order to handle this from a code standpoint, here's what happens, okay? So the first thing that happens is we derive a generic expression for the buckling capacity of not a beam, but a plate, okay? So I'm not going to expect you to go through that. That is a very lengthy derivation. That's a grad school derivation. I didn't see that until grad school, and to get into that, you'd have to discuss plate theory and partials and series, and yeah, I'm not getting into that. But there's a couple things that you should be aware of for this expression. So first off, for now, just sort of trust me that this expression works, and let's just sort of take a look at it. So it's a function of a couple things. So first off, it's a function of E, which is 29,000 KSI for steel, right? Everybody's aware of that, okay? It's a function of B over T. B over T is your width to thickness ratio. In other words, that's sort of a measure of how flimsy your plates are. Like if you have a really, really high B over T ratio, that means you have a really thin flange or a really thin web. So that's sort of our mathematical way of expressing whether or not the flanges or the webs are flimsy. They're either really stocky or really flimsy. Okay? Now it's a function of this value here, this value nu, Okay, we have a name for that. We call that Poisson's ratio. Now, does anybody remember what Poisson's ratio is, like behaviorally? Go ahead. No. Exactly. It's exactly right. So if you have, let's say, a rubber band or a piece of taffy or something like that, and you yank on it, not only does it get longer, but it gets thinner. And vice versa, if you press it, not only does it get shorter, but it expands. Okay? And the ratio between the strain that you get laterally versus the strain that you get longitudinally is what's called Poisson's ratio. Now that is a material parameter. Steel has a Poisson's ratio, concrete has a Poisson's ratio, every unique material has a unique Poisson's ratio. For steel, for structural steel, that value is always about 0.3. Okay, that's just a constant. You don't have to memorize that. You don't have to memorize that. I just want you to see what that value is. The last parameter here is this term K. Now you can kind of think of K as like a critical, like an effective length factor. It's not quite the same, but it's kind of close. But let me talk about K. Okay. This equation here, the way it works is it will tell you the critical buckling stress as a function of these parameters. Okay. So let's say we're dealing with steel. So that's a constant and that's a constant. So there's really only two things you can vary. You can vary this, so you can start making your plate thinner or thicker or whatnot, and you can vary this. Now here's what ends up happening. What we have is we have a plate strip that sort of goes on forever, and we're applying compression to it. Now what we're doing in our analysis is we're assuming that this edge and this edge are simply supported. Okay? And every time that we do a buckling analysis, we assume that. But what we're not talking about is what's going on with this edge and what's going on with this edge. Okay? So for this image right here, this would be a free boundary condition. In other words, this edge is free to do whatever the heck it wants, and this edge is free to do whatever the heck it wants. Where the real value in this analysis comes from is what if we start changing what's going on each edge. So for instance, this is B and this is T right here. Okay, so I'm looking at the plate this way. And so when we perform this buckling analysis, what we do is we start changing what's going on the side. So one thing that we can do is we can assume that this side is completely simply supported, and we can assume this side is completely supported. That would be one way we could do the analysis. Another way we could do the analysis is to assume maybe this side is fixed, and this side is fixed. Maybe another way of doing it is to assume that this side is fixed and this side is free and it's just allowed to do whatever. And so what I mean by that is, let's say we're talking about this one on the bottom. What I'm doing is I'm assuming that this entire edge is fixed and this entire edge is free, and so that's going to change the way that the plate is going to buckle. I mean, imagine if I took the plate as if it was free and I pressed on it, the whole thing is just going to bend like this. But if I clamp this edge over here, it's not going to buckle like that. Maybe this side dips down a bit, but the side on the left stays fixed. Is everybody okay with that? So what you can do is this. You can say, all right, what I'm going to do is I'm going to look at all of those different cases. And so what you've got here is this graph showing what happens when you start varying these cases. So like case A is if you fixed one end and fixed this end. Case B is if you fixed one end and this end simply supported. Case D, free and fixed, free and simply supported. So this is just testing all of the different parameters and variations. So for each of these cases, what they're doing is they're making the plate thinner and thinner and thinner, and they're computing how much stress it would take to buckle it. And so does everybody notice for these curves that something weird kind of happens? Like depending upon how thin the plate gets, see how it kind of floors off? See how it kind of caps off there on the bottom? Like if we're looking at KC, it never quite gets below like 4. Does everybody see that? For case B, see how it never quite gets below something like, what was that, like 5.5? Something like that. Does everybody see that? Yes. That's a good question. So what's actually happening is because, I mean, if you looked at the equations that go into this, they're pretty nasty. What you're seeing is basically like a bunch of parabolas lumped on top of one another, and we're only taking the minimums. So so there's like a curve here, and then a curve here, and then a curve here, and it's just taking the minimums. Again, I don't expect you to memorize all the math behind this because it gets a little messy. But what I really want you to pay attention to is that for each case, see how there's kind of a minimum, there's kind of a worst case scenario. Okay, here's why that's important. So if you're looking at each one of these cases, like if you see over here on the right, these are the minimums. So for instance, case C, you can see how case C never really dips below 4. You can see how case B never really dips below something like 5.5. The actual value ends up being like 5.42. Everybody okay with this? Okay. So here's what I'm going to do. I'm going to take this equation. First thing I'm going to do is I'm going to rearrange it. And I'm going to rearrange it to where I'm putting basically everything on one side of the expression. And I'm saying that this whole big ratio has to be less than or equal to 1. Okay? What happens is when you plot that, you get an equation that's very, very similar to that elastic buckling curve that we saw earlier. But like columns, plates have inelastic capacity as well. So really what we end up doing is that it would make sense theoretically to limit that ratio off to 1. But if you actually start testing plates, you'll see that they actually have an inelastic capacity a little lower than that. So what we do is we back that off to 0.7 to account for the way that plates really behave. And then we say, all right, let's back that off to 0.7. Let's rearrange this expression to solve for this. Okay? So we solve for this, so we get this expression up here, and everything that's under this square root is something that we can just plug and chug, because that's pi, that's 12, that's 1, and that's 0.3. So plug and chug, and you get this expression. Okay? This is actually pretty powerful, okay? Because what we're saying is that we can determine whether or not local buckling is going to occur, and the only thing we have to do is we have to look at these B over T ratios. Okay? The only question that we have to answer is what's going on with K. Okay? And the way that we answer that in the spec is we define 2 different types of elements. Okay? I want everybody to turn to this table here, this 16.1-17. So 16.1-17. Here, I'll write it up here. You'll see why. Okay. Has everybody brought their AISC 15th edition steel construction manual with them, right? Now, it's a little difficult to read, but do you notice over here on the very, very left of the table, if you kind of turn the table over, does everybody see where it says unstiffened elements and stiffened elements? Does everybody see that? Okay, so the difference between an unstiffened element and a stiffened element is that a stiffened element is supported on both sides, whereas an unstiffened element is only supported on one side. So for instance, if I was looking at, let's say, an I shape, the flange would be considered an unstiffened element. And what we're looking at is that, bless you, what we're looking at is that outstanding portion of the flange out here. And so what we're doing is we're looking at that width to thickness ratio, and we're basically saying, okay, if we took this column and we pressed on it, is this plate going to buckle on its own? Okay? And so the way that we do that is we compare that B over T ratio to this. Okay? Bless you. All right? So we've got 2 different elements to consider, stiffened and unstiffened. So unstiffened element would be, so this would be unstiffened. This would be like the flange, the leg of an angle, the outstanding elements of a T shape, anything that's only supported on one side. Whereas the web of an I shape, or maybe the web of a channel, would be something that's stiffened because it's supported on both sides. So what we do is we consider the type of element we're looking at, whether it's unstiffened or stiffened, and then we try and determine the appropriate value of K. How do we determine the appropriate value of K? Well, let's take a look at an unstiffened element. An unstiffened element's one that's only supported on one side. So I guess the question is this a fixed boundary condition or is it a pinned boundary condition? Well, a fixed free boundary condition uses a K value of like 1.28. A pinned boundary condition uses 0.43. Let's just go, I don't know, a third of the way in between. Is this fixed? Is this pinned? Probably neither. It's probably somewhere in between. So we assume a K value of in between, something like 0.7, plug and chug, and we get this. Okay? For stiffened elements, is this fixed? Is this pinned? I don't know. It's probably somewhere in between. So fixed is 6.97, pinned is 4. We'll assume somewhere in between, something like 5, plug and chug, and here's what you get. I don't expect you to understand where these equations were derived from. But is everybody kind of understanding what I'm doing here? Okay. If you go to the spec and look at case 1, what do you have? 0.56. If you look at case 5, what do you have? 1.49. 0.56, 1.49. So that's where those values are coming from. So this is actually like a really, really powerful tool within the spec because I'm going to go ahead and tell you, the math behind local buckling is very, very complicated. What we end up doing is we say, all right, an easy way to handle it is just to check whether or not a shape has a really, really flimsy flange. How do we do that? We compare its slenderness against this limit. If we're less than that, we're good. If not, we have to consider local buckling. A while back, I don't remember who it was, but somebody asked me a question about there was a, if you go to the W shapes and you start turning through the pages, you start seeing these little notes, like the little C value and the little C or the F value next to it. Does anybody remember that? Like if you start turning through the W shapes, like everybody turn to page, let's say 1-16. I just made that up. Turn to 1-16. Okay, now I'm going to pick a random shape. Let's pick a W30 by 148. Does everybody see that? Does everybody see the little note C? Everybody see that? Okay, now what does that note C say? It says the shape is slender for compression with Fy equals 50 KSI. Does everybody see that? What that means is that for that particular shape, if it's 50 KSI, what that means is if you load it, it's going to locally buckle before it globally buckles because of the way that shape is arranged. That particular shape has either really flimsy flanges or really flimsy webs under compression. Now, a couple things worth mentioning, these limits change whether or not you're talking about members in compression or members being bent, and it also changes depending upon your steel. If you have a different Fy value, you're going to get a different limit. Now, I'm sure some of you are like, let me say this. I'm going to make you check this for every problem that we do. And I'm sure some of you are going to be like, that's dumb, Dr. Mike. Can't we just look at the shape and it says it's not slender, so we're good? Why do we have to go through and do all this math? I can understand that. The problem is if you're doing something, let's say if you're in bridge land and you're designing, let's say, a plate girder, there is no table to tell you whether or not the plate girder is good or not. You basically have to go through and check all of these limits. So I'm making you check them so that if you all get into designing, let's say, bridges, or you get into designing sections with custom cross sections, that you know how to do this. I'm sure some of you are going to be like, this is a waste of time. I understand. I'm still making you do it. So, yes? That's a great question. So the question was, what's the difference between a built-up I shape or a rolled I shape? The difference is, so you might hear me use the term plate girder versus a rolled beam. That's basically the difference. So rolled beam are basically the W shapes that come out of the manual. We take a steel product and roll an I shape. A built-up shape is when you're taking plate, plate, and plate and actually welding and creating a custom I shape. That's what we mean by built up. You're actually creating one. In Bridgeland, that's very, very common for fairly long spans because you're customizing the shape of the flange and the web to meet your load demand. Whereas in buildings, the loads just aren't that big. You don't need that level of customization, so you just use shapes that are rolled. And believe me, there's plenty of shapes in here to choose from. So, yeah. Sound good? Okay. So like I said, I am going to make you go through this analysis. Now, one thing to keep in mind, a local buckling analysis is really easy. All you need are two ratios. You need the flange slenderness and you need the web slenderness. Fortunately, if you look on your I-shapes, table 1-1, they're right there. See over here on the right where it says compact section criteria? They're right there. So you have the flange slenderness and the web slenderness already computed for you. You don't have to go out of your way to compute it. If we were looking at, let's say, a plate girder or something like that, we would have to say, okay, BF divided by 2TF and D over TW or what have you. For here, we don't have to worry about it. They're already computed for us. That makes our life a little easier. Everybody with me on that? So step one, first off, we determine whether or not we have slender elements. Now, if I have a section that fails, that means it's susceptible to local buckling. Does that mean that the section is unusable, that if I put a feather on it, it's going to explode? No, it doesn't mean that the section's unusable. All it means is that we have to use different equations. So if you look at the spec, we're going to mainly be operating in section E3. Section E3 is flexural buckling of members without slender elements. So that's come on. So this is chapter E3 or section E3. So if you do not have to consider local buckling, you're using the equations that we've presented before. And let me be clear, 99 out of 100% of the time, you'll never have a situation where you don't use section E3. This is what you're going to be using just about every time, for the most part, even in practice. When I say that, I'm talking about like column design and beam design in buildings. In bridges, that's a different story. Let me go back. Hello. Okay, so step one is to determine whether or not local buckling is going to be a concern. I understand this is going to be a formality for most of our problems, but I do want you to go through with this so that you're aware of how the spec works. So we're going to check whether or not the section contains compact elements. Spoiler alert, most of the time they are not going to. And then we're going to determine the capacity. Now, there are essentially three different ways to compute the capacity of a section according to the manual. We're going to do all three of them, okay? Now, what ends up happening when you use each of these methods is that they give you slightly different answers. The only reason that you get different answers, though, is because of rounding, but theoretically they would give you the same answers. The first method is to use the equation straight out of the spec, and that's what we're going to do first, and then we're going to use a couple of design aids, okay? Now, like I said, the first method is basically to use these equations that come straight out of the spec, and so that's what's going to be the focus of our first example. However, we have to talk about slenderness first. Everything that I've been talking about before, if some of this math regarding local buckling has lost you, that's actually fine because in practice, it's really, really easy to handle, okay? What is difficult to handle, and I don't want to say difficult, but what you really need to pay attention to is slenderness, okay? Now, how do we define slenderness? Slenderness is defined as essentially L over R, right? Right? So the length divided by the radius of gyration. Now, when you've got a W shape, there are two radii of gyration. There's the Rx value and the Ry value. The radius of gyration about the strong axis and the radius of gyration about the weak axis. And they're referred to that way because Rx is always bigger than Ry. I've mentioned this before. So the question comes, do we ever have to check the strong axis? I mean, if if you're doing L over R and RY is always smaller, do we ever have to check RX? Do we ever have to check the x-axis? The answer is yes, okay? The easiest way to explain why is to look at this column over here, okay? Now, what I have here is a column. Now, the physical length of this column is 35 feet, okay? The bottom of this column is fixed, and we're going to consider the top of this column is pinned, like it's allowed to rotate. These elements will prevent it from moving, but not rotating, whereas this on the bottom, that's fixed in, and that's not only moving, that's not rotating. Now, here's the thing. This column is braced. Everybody see you've got these bracing, these elements framing in. We have one coming up 10 foot off the ground, one 15 foot off of that, and another 10 feet. So really what's going on is we've got two different situations depending upon which axis we're looking at. Everybody's can probably see that along the strong axis, this column is completely unbraced. So its length in the L over R count, its length would be 35 feet. Whereas along the weak axis, the length isn't 35 feet. Well, really, we have three of them. We have a 10-foot section, a 15-foot section, and a 10-foot section. So here's the thing. It's not a matter of whether or not Rx is bigger than Ry. It's about what the biggest L over R value is. It's about what the biggest slenderness is. Remember, as slenderness goes up, capacity goes down. So what we end up having to do is finding the worst case slenderness value. So you have to check both axes, okay? What we end up doing from an analysis perspective is we split a column like this into something like this. So here's the column, and what I've done is I've split it up into two segments. So over here, this is the x-axis. Over here, this is the y-axis. So I'm calling this the x-axis because if the column were to buckle this way, it'd be buckling about its strong direction. Here, it'd be buckling about its weak direction. Now, does everybody kind of understand what's going on with these symbols? So here, what I'm seeing is that's the web, and then here's a flange, and here's the flange. So we're sort of looking at the web, and this is the strong axis. Over here, we're looking at the top of the flange, and those two dotted lines are the web, looking through that. So it would be as if our eye was looking down. We would see the flange, and the web would sort of be sticking right there if we could see through the plate. Does that make sense? So along the strong axis, we have a length of 35 feet. Along the weak axis, we have lengths of 10, 15, and 10. We kind of have to check all of them. And you'll see why. It'll be pretty easy to see how you can eliminate some, but we'll get into that here in a second. Speaking of, why don't we actually analyze this column? Okay, so I'm getting sick of talking. Let's do some math. So I have this this column. We're going to say it's a 14 by 90. Okay, it's a 14 by 90 column. It's here's the length. So the strong axis bracing on the left, the weak axis bracing on the right. It's a 50 KSI column, and what I want to do is I want to determine ultimately what is the capacity of this column. This is going to be a somewhat detailed example. Don't worry, I'll take my time with it. I've really information overloaded everybody. I can understand that. Don't worry. It's not so bad. Okay. Ooh, that's long. Ooh. Okay. All right. So this is example 15A. Now we know that Fy is 50 KSI. That was given to us. Now we also know this is a W14 by 90. Okay. I'm going to walk you through this a little bit. I'm going to need some properties for this W14 by 90, and I'll walk you through what we need. We're going to need the gross area. We're going to need Rx and Ry. Let's start off with those. We're going to need two more, but let's just start off with those. Sorry, say that again. 26.5, okay. Now what page are you on? 1 dash what? 24. Okay. So we'll say page 1-24 and 1-25 because the RX values are on the other page. So this was 26.5 square inches. And somebody else tell me what RX is? 6.14. What's the dimension? And somebody else tell me what RY is? 3.7. So this is 6.14, 3.70 inches. Everybody okay with that? Now we're going to need two more quantities, and those are the slenderness values. So we need BF over 2TF, and we need H over TW. Okay? Now, what are each of those values? Somebody tell me. 10.2 and what? 10.2 and 25.9. What are the units? There are no units. This is a slenderness value. Slenderness values are unitless. Like this is inches over inches, inches over inches. So slenderness values are always unitless. Okay. Now, what we've got to do before we do any analysis is we have to determine whether or not local buckling is a consideration. So I'll do this over here on the right. We'll say consider local buckling. Okay. Another name for this is, like, there's another name for it. We could sometimes call it compact section criteria. So if I refer to both, just bear with me. And if you're still a little lost, don't worry, we'll get there. Okay. Now, what I want to do is I want to go to that table we were just looking at, page 16.1-17. Now, we have unstiffened elements and stiffened elements. Of the unstiffened cases, does everybody see which case we would look at? Case 1, case 2, case 3. There's 4 cases. Which one are we going to look at? Case 1. Case 2 is for built-up sections. We're not looking at that. Case 3 is looking at angles. Case 4 is looking at T's. So we're going to look at case 1. And so what we're computing is a lambda RF of what? So that's 0.56 29,000 over 50. So what does that come out to be? I'm just curious. $13.5 a second. Okay. Now, let me explain how this works. Okay. Let's just talk about slenderness in general. The larger the value, the more flimsy the shape, right? Okay? Now, what this is telling us is that if your flange gets more slender than that, you've got local buckling problems. Now, how slender actually is our flange? What is our BF over 2TF? What was that? 10.2. So what this is telling us is this is our actual slenderness. This is the limit. If we go over this limit, then we have to consider local buckling. So do we have to consider local buckling? No. So that's what we're after. We're after our actual slenderness being less than these limits. So what is lambda RW? What's the other one going to be? So in stiffened elements, we got case 5, 6, 7, 8, 9. Which case are we going to consider? 5, right? We don't have HSS. We don't have cover plates. We don't have any other stiffened elements. So case 5. So 1.49 square root of E over Fy. 1.49 square root of 29,000 over 50. And that equals what? 35, we'll say 35.9. Second. And so what is our H over TW? It was 25.9, right? So is that good? That's good. Now again, you could have said, well, Dr. Mike, there wasn't the little C note on the W14 by 90, so why did we have to go through all this? You do on bridges, so that's why. I'm trying to get you used to that, because when you start evaluating bridge girders, you have to go through all of this. I want you to be familiar with it. Yes? What do you mean? Well, it says that it'll say the shape is slender for 50 KSI steel. It'll say that. And that's another reason why you would need to go through this exercise is what if you're using 70 KSI steel or something high grade? It's a very good point. Hence, all the more reason to do it. So, okay. Everybody good? Okay. Now, before we start computing capacities, we need to look at slenderness. All right. Now, I'm lazy, so I'm going to copy this down again. Now, how do we generally compute slenderness? Like, what is our general term? We need 3 quantities. We need a length, a radius of gyration, and what? Say it again. Louder. K factor. There you go. We need a K value. Okay? So, does anybody remember where we get K values? 16.1-570. This is where these tabs are coming really, really in handy. So, (16.1-570). We're way back into the the gray section of the commentary. Okay. Now, let's take each of these segments one at a time. Let's start off with the x-axis. What does the bottom look like to you? Is that free, fixed, pin? What is that? Okay, and the top? So what would the K value for this segment be? Oh, read that closer. Read that more closely. Say it again. Why'd you change your answer? There you go. There's theoretical values, but then there's recommended values for design purposes. So for this segment, we're going to say Kx is 0.8. Does everybody see that? If you don't, please, I mean, don't just go, well, I'll just figure it out later. You know, I don't want to raise my hand. No, raise your hand. So, does everybody see that? What case, what letter? B, right? We're on case B. Does everybody see that? Okay. Now, for the column over here on the right, what I've got is I've got 3 segments. So what I'm going to do is this. I'm going to say, what I'll do is I'll say this is KY1, this is KY2, and this is KY3. let's start off with KY1. What's our K value going to be for this boundary condition? I couldn't hear it. 1, right? What about for 2? 1, right? What about for 3? 0.8. Does everybody see that? So this is 1, 1, and 0.8. And so when you do this, what you're going to do is you're going to repeat this calculation for as many different bracing lengths as you have. The x-axis, what you're after is this. You're trying to determine not the longest length, not the biggest K value, or not the biggest radius of gyration. What you're trying to figure out is the biggest KL over R. Okay? So we're going to compute 1 KLR over here and 3 KL over R's over here. Let's start off with the x-axis. So remind me real quick, just so I have it up here, what was Rx and Ry? So, that's 35 feet and that, right? Why are you shaking your head no? That's exactly right. This is in feet, this is in inches. So what does this come out to be? Say it again. 20.52? All right, say that again. Give me a couple more. All right, do I have a second on that? Okay. All right, let's keep going. So we've got 3 of these to compute on the y-axis, and then we're going to call it after this because we're running out of time. So I'm just going to do each of these one at a time. So this is 1, 10, this is 3.7, 1, 15, 3.7, then 0.8, 10, 3.7. And this is 12 inches per foot. Now, does anybody have some answers for me? How about for 1? 32.432. What about for number 2? And for the next one? No, say it again. 950? Okay. All right. Everybody see what we did? Remember, this one has a different K value. All right, does everybody see what we did? Now, let's go back in hindsight. Did we really need to do 1 and 3? Like, think about it. This one not only had the longest segment, but it also had the largest K value. So is it any big surprise that segment number 2 had the biggest KL over R when you compare it to 1 and 3? Really no point, right? You could have just looked at it and said, well, I'll just do 2. But now you see that since we've done it. Now, let me ask you this. Of all of them, which is the worst case scenario? Remember, what's the deal with slenderness? Larger slenderness equals weaker section. So what's the worst case scenario? The x-axis. So what we're going to find, and just so everybody's clear, we're going to be doing a lot of math on Wednesday, but just so everybody's clear, the x-axis governs. If I load this column, it's actually going to buckle about its strong axis, not its weak axis. But that'll become clear when we do start digging into our calcs on Wednesday. That's all I have, everybody. What? What'd you get? Say it again, 48.649. Okay, but it's still governed, so that's all I got.